All right, on to the second half of Chapter 1 of Physics on the MCAT. And just one small note before I begin, I am making a comprehensive physics equation sheet for the MCAT, so essentially one page that features every physics equation that you have to know. And if you'd like a copy, either comment your email down below and I'll send it to you, or send me an email, which I'll have in the description below, and I'll be happy to send it to you. We'll begin once again very briefly with the SI units. And for the most part, it's going to be the same as the first half of this chapter. Just one addition that I'll make here quickly is force. Force is going to be a key concept that we'll discuss throughout the rest of this video. And force is measured in newtons, which has a symbol capital N. And newtons can also be expressed in the SI units that we've already covered. So the equation for force is mass times acceleration, or F is equal to ma. And mass has the units of kilograms, while acceleration uses meters per second squared. So force can be expressed in kilograms times meters per second squared. Okay, so let's talk a little bit more about forces. A force is a vector quantity, and it's important to look at all the forces on the object, which is essentially the net force. If the net force is equal to 0, then an object with a mass is going to have an acceleration of 0 as well. That means that when the net force is 0, an object will stay at its current velocity. And that is Newton's first law, or the law of inertia. And all this means is that unless a net force acts upon an object, the object will either stay at rest or it'll stay in motion at its current velocity. And Newton's second law is what we just described with this equation, F is equal to ma. And this is in a sense the opposite of the first law and states that when there's a net force acting upon an object, it will accelerate according to this equation. And finally, Newton's third law states that with every action exists an equal and opposite reaction. And in terms of forces, this is saying that when one object, for example, box A over here, exerts a force on box B is actually going to exert the same force back to A. And a common application of this is the normal force, which we'll talk about on this next slide. So let's take this very basic example of a man standing on the ground to illustrate all the forces at play, as well as the applications of the three Newton's laws that we just discussed. And before we do all that, I want to quickly make a distinction between mass and weight. So mass is an inherent characteristic, and that's basically the amount of matter contained within an object, or in this case, a person. So the mass here is going to be, let's say, 75 kilograms. And the mass of this man is going to remain the same whether he's on Earth, he's on Mars, and would only change after something like an all-you-can-eat buffet. The weight, however, also depends on the gravitational field in which he's located. So on Earth, gravity results in a downward acceleration of 9.81 meters per second squared. So 9.81 is the value for A on Earth. Now, when we talk about the weight here, we're actually talking about the downward gravitational force at play. And we know that force is equal to mass times acceleration. So the relevant force of gravity here is actually equal to the mass times the acceleration due to Earth's gravitational field, or 9.81 meters per second squared. So the weight of this man is actually 75 times 9.81 meters per second squared, or 736 newtons. And this man's weight would not be the same if he was in a location with a different gravitational field. So Mars or the moon, for example, this man would have a different weight than he does here on Earth. The next thing that I want to touch on is friction. And friction is a fundamental force that always resists motion. So friction opposes motion in two different ways. There's static friction, which prevents the initiation of motion. And there's kinetic friction, which resists ongoing motion. So I'll give a quick example of what that means. Let's say we have a box over here that's going to be sliding along the ground. Okay. When we first apply a force to push this box, the force of static friction is going to resist this force and act in the opposite direction. And this is what's going to keep the object at rest until we adjust our force, or the force of pushing exceeds the force of friction. Because again, we have to have a net force acting on the object for it to move. If the forces cancel out and the force of static friction is the same as the force in which we push the box is not going to move. So again, the force of pushing must exceed the force of static friction to initiate motion in this direction. And the equation that we use for this is the force of static friction is equal to the normal force, which is, again, the weight of the object, or mass times 9.81, multiplied by the coefficient of static friction. That's just a constant that depends on the actual surface. So a rougher surface, for example, would have a higher coefficient of static friction, and a smoother surface like ice might have a lower coefficient of static friction. So let's take an example here. Let's say that this box weighs 50 newtons. Okay. And the coefficient of static friction of this surface is 0.8. This means that the maximum force of static friction is going to be equal to 50 multiplied by 0.8, or 40 newtons. So we see that the maximum force of static friction is equal to 40 newtons. And that's going to be the force that opposes motion, or the force that opposes our initial push to get the object moving. So essentially, we have to exert a force, or a pushing force, of greater than 40 newtons to create a net force to push the object forward. And when we now talk about kinetic friction, it's quite similar, but one key difference is that static friction is not always going to be a constant magnitude. So static friction essentially matches the force that we push the object with. So if we give it a slight push, let's say we give it a push of 10 newtons, then the force of static friction will be 10 newtons as well. And that's going to build up and match the force that we exert until we reach the threshold, or the maximum force of static friction, at which point we will have a net force and the object will begin to move. But with kinetic friction, the value of the force is constant. So kinetic friction acts when an object is already moving. So let's take this box over here. Let's assume that it has already begun moving. We've already overcome the initial static friction, and it's moving along this ground. As it's moving, we're going to see a force of kinetic friction that opposes this motion. So once again, it's going to be acting in the opposite direction, just like that. And the equation for this is almost the same. It's going to be the force of kinetic friction is equal to, again, the normal force multiplied by the coefficient of kinetic friction. And one thing that's interesting to note is that the coefficient of kinetic friction is almost always going to be lower than the coefficient of static friction. And that's why when we move something, we can often see that it's easier to keep it moving than it is to initially get it moving. Like once we overcome that first kind of hurdle and the object begins to move, it's easier to keep it moving than it was to initiate the movement. And as we see in the equation, the force of kinetic friction does not depend on the velocity of the object or how fast we're moving it. All it depends on is the weight of the object, the normal force, and again, the type of surface, which has a characteristic coefficient of kinetic friction. Okay, now we're going to apply this to a little bit of a trickier scenario, and that is the inclined plane. So what makes these a little bit harder is that you have to use some trigonometry to be able to solve for this, and that'll become apparent once we start to look at all the forces at play. So as always, the main force that we start with, or that we know exists here, is gravity, right? And gravity always exerts a force directly downward. But because this inclined plane is at an angle, we know that gravity is going to do two things. It's going to exert a perpendicular force downward, just like that, which is the force that the box exerts onto the plane. And we should then see a normal force that opposes that, right? So we should see a normal force that goes upward and is the force that the inclined plane exerts back on the box in an equal but opposite fashion. But the force of gravity is also going to push the box downward, or down this plane. And in the same way, that is going to be opposed by a different force, the force of friction. So this all looks quite messy, but this is actually quite an important skill to have. And this is called a free body diagram, which is where you basically draw out all the forces at play here. And for something like an inclined plane that's at an angle, this is especially helpful. So now let's take a look at the tough part of this. When we look at the force acting perpendicular to the plane, so the component of the gravitational force that is acting from the box downward onto the plane, that is going to be equal to mg cosine of theta. So m times g is just the force that we always use for the force of gravity pushing an object downward. But because it's at an angle here, we're going to use mg cosine of theta. And in just a second, I'll show you a trick on how to remember when to use cosine and when to use sine. But in the opposite way, the force the component of gravity that's pushing the box downward, for that force, we're going to use F is equal to mg sine of theta. Okay, and how do you remember which one is which? So the way that I like to remember this is just by knowing that as this angle over here increases and approaches 90 degrees, the plane gets steeper. And when it gets steeper, we see, or we should see, this force increase. We should see the box slide down faster. So this value over here, the force that's pushing it downward, should increase as the box gets steeper or as the angle approaches 90 degrees. And sine is what increases as we approach 90 degrees, whereas cosine decreases. So if sine is the one that increases as the plane gets steeper, then that's the force that we want to be using for the one that pushes the box downward. And if the math here itself is a bit confusing, let me know in the comment section down below, and I'll be happy to make a few videos explaining the math behind all of this. But I hope this makes sense in terms of when to use sine and when to use cosine, as well as all the forces here that are relevant. So just to recap, we have 4 forces here. We have the component of gravity that pushes the box down the plane, and that's countered by an opposing force of friction. And then we have the component of gravity that pushes the box into the plane, and we have the opposing normal force that is equal and opposite and is perpendicular to the plane pointing upward. So those are the 4 relevant forces in an inclined plane. Okay, one more application of forces and the fact that when the net force is not 0, things start to move is torque. And we look at what we call rotational equilibrium. So let's take a classic example of a seesaw where we have some kind of a lever that's going to rotate along a point. All right, so this over here is going to be our point of rotation. So the forces that act upon here are going to be acting in a perpendicular manner. And what I mean by this is, let's say we have, some kids sitting over here on the seesaw. It's a big seesaw. Those kids are perpendicular to the seesaw, right? The kids are vertical and the seesaw is horizontal. And these kids who are sitting perpendicular to the seesaw are exerting a torque on the seesaw. And the sum of the torques must be 0 for the seesaw to remain in rotational equilibrium. So let's look at the equation for torque. Torque has an equation of the radius times the force times sine of theta. So the radius is the distance between the object and the point of rotation. So that's this point over here. It's the distance between, in this case, the kid and the center of the seesaw. And that should be in meters, which are the SI units for length. The force is the downward force that the kid exerts on the seesaw, which is the force of gravity, as we've already covered. Mass times gravity, or the child's mass in this case, times 9.81 meters per second squared. And sine of theta just refers to the angle of the child compared to the seesaw, or the angle of the object compared to the lever. So in this case, it's a 90-degree angle, right? The child is perpendicular to the seesaw, and that's when we see a maximum torque. If the object is fully parallel to the seesaw, then we don't see a torque. And there's a maximal torque when the object is perpendicular to the lever. So what we see here is that torque is proportional to the radius, or the distance from the object to the point of rotation. So the longer the lever, the higher the torque. If we were to move this point of rotation, let's say somewhere over to this side, now we might have something like, let's say a 3-meter distance over here. And from here to the other child, we can say is a 7-meter distance. So for the torques to balance out, this child must have a higher mass and therefore a greater downward force to balance out the torques. And that does it for the first chapter of physics on the MCAT. Here's a list of equations that we covered in this video. The key though for this topic is really to be able to combine all these equations and to apply these to many applications of these questions. So, being able to learn the content this way is one thing, but I highly recommend that you supplement this with as many practice questions as you can. So we basically just covered the first chapter of the Kaplan textbook. So if you do have the textbook, the end of chapter questions are a good way to do that. But one thing that I will say is that there are certain concepts covered in the first chapter of Kaplan that aren't tested on anymore on the MCAT, such as circular motion. My other recommendation is UWorld. They have an excellent and really comprehensive question bank for the MCAT. Not sponsored, but I use them and really had a great experience. Again, make sure you know these equations, but more importantly, how to apply them. Hope you found this helpful, and I'll see you soon for chapter 2.